Hello, my name is Daniel Chaver Martinez. I'm an associate professor at the University Complutense of Madrid, and in this talk I will present the RVfpga package and several teaching experiences that we've had in the latest months based on this course. This is the outline for the talk. We'll start with an overview of RVfpga, where we'll describe the RVfpga course software and hardware. We'll give an overview to the labs, and we'll talk about extra resources. Then we'll explain several teaching experiences using the RVfpga package, starting with official courses, then bachelor and master thesis, and finally MOOC courses and micro-credentials. Finally, we'll end with talking a bit about collaboration opportunities. Many persons, companies, universities, institutions have contributed to the RVfpga course that shows how to target the VIR commercial RISC-V core and VIR-Wolf system on chip to an FPGA and to simulation tools. Also, how to program the RISC-V SoC, how to add more functionality to the RISC-V SoC, such as new peripherals, instructions, etc., and how to analyze and modify the RISC-V core and memory hierarchy. The package has been developed by Imagination Technologies and its academic and industry partners, and after completing the RVfpga course, users will walk away with a commercial RISC-V processor, SoC, and ecosystem that they understand and know how to use and modify. Imagination Technologies offers two courses: the RVfpga course, a first course about the RISC-V core memory system and peripherals, and their RVfpga SoC, which is a second course that shows how to build a RISC-V SoC from building blocks, install the Zephyr real-time operating system, run programs on Zephyr, and run simple TensorFlow programs. Both courses are available as separate downloads from this link. To use RVfpga, you need to install either Platform.io, which is an extension of Visual Studio Code with the Chips Alliance platform, or the Catapult SDK. Besides, you need some other tools such as Verilator or GTK Wave, and you also need to install Vivado in case you want to make changes to the SoC for the FPGA. There's complete support for Linux, and most things are also supported in Windows and Mac OS. As the optional hardware, 3 FPGA boards are supported: Nexus A7, Basis 3, and Boolean, but remember that everything can be run in simulation. And the core used is the VIR, both EH1 and EL2 cores, and the VIR-Wolf SoC, which is based around these two cores. This slide illustrates the RVfpga hierarchy: the EH1-EL2 core, the EH1-EL2 core complex, the VIR-Wolf extended SoC, and the implementation on different FPGA boards, Nexus A7, Basis, and Boolean, and in different simulation tools, RVfpga Trace, Vidbo, Pipeline, and Whisper. Here we show the complete RVfpga system, which is based on the EH1 core, in this example. Then it is surrounded by the VIR EH1 core complex, which adds some elements to the core. This is implemented in the VIR-Wolf X SoC, an extended version of the VIR-Wolf SoC, and these can be targeted to the FPGA, in this case a Nexus board, or to a simulator. The VIR EH1 core and core complex is an open source core from Western Digital. It's a 32-bit superscalar core with dual issue 9-stage pipeline. It has support for the base ISA as well as the compressed and multiply extensions. It includes separate instruction and data memory tightly coupled to the core, as well as an instruction cache. It also includes a programmable interrupt controller, core debug unit, and the system bus has both AXI4 or AHB Lite buses. The EH1 core complex is included in the Virwolf extended system on chip, which adds several elements to the core. Specifically, it adds a boot ROM, a system controller, an SPI controller, and a UART. And for RVfpga, we've included some extra controllers such as another SPI, a PTC, and a GPIO. The peripherals use a wishbone interconnect, so an AXI to wishbone bridge is also necessary. RVfpga has support for different tools. All of them share a common backend, which is the Virwolf SOC we've just explained, but the front end is different. If we have an FPGA, we can use Vivado to generate the bit stream for the FPGA, in this example the Nexus A7, and we can also use RVfpga in simulation. All the simulators use Verilator, and we have three of them: RVfpga Vidbo, RVfpga Trace, and RVfpga Pipeline. We'll explain them next. In this slide, we show RVfpga Nexus, which adds several elements to the Virwolf SOC. It adds a DRAM controller, a CDC, a vSCAN for the JTAG port, and a clock generator for a frequency of 50 MHz. The RVfpga Nexus uses several peripherals in the board, such as a DDR2 memory, UART via USB connection, SPI flash memory, an accelerometer, the 7-segment displays, and the switches and LEDs on the board. Most of you probably are familiar with the Nexus A7 board, which contains an Arctic7 FPGA, includes many peripherals such as LEDs, switches, push buttons, and some others, and is available for purchase at DigiKey or Digilent and other vendors. The RVfpga Trace simulator generates a trace of the internal signals of the SOC while executing a given program. You can visualize the waveform of this trace with GTK wave. Any of the SOC signals can be selected and visualized in the waveform. For example, in this figure, we illustrate the waveform of a multiply and an add instruction flowing through the 6 final stages of the Vir EH1 pipeline. The RVfpga Vidbo simulator uses a virtual development board to perform a simulation of the RVfpga system and communicate with the peripherals. The virtual board visualizes the simulation on a virtual FPGA board in a web browser. In the program executed in the figure, if you click on any of these switches, the corresponding LED will change the state. So, for example, these 4 LEDs are on because the corresponding switches are up. Finally, the RVfpga pipeline simulator shows the instructions of a RISC-V program flowing through the 6 final stages of the Vir EH1 pipeline. It uses as the front end GTK to show the instructions and signals in the pipeline stages. For example, in this case, we see several instructions flowing through the 6 final stages of the Vir core and the main signals in each of these stages. For the EL2 core, we provide exactly the same tools, but given that this is a smaller core, it fits in smaller FPGA boards, such as Basis 3 and Boolean board. The Getting Started guide is the introductory document of the RVfpga course. It starts with an overview of the RISC-V architecture and an analysis of the RVfpga system. Then it provides in-depth instructions for the 3 supported operating systems on how to install the tools used in the RVfpga course: Vivado, Platform I/O, or Catapult SDK, simulation tools, board drivers, etc. It also provides detailed instructions about how to write, simulate, and run programs on the RVfpga SoC using 7 example programs. You can see in the table these programs. These example programs are executed both in simulation and on the FPGA boards. You can use the bit streams and binaries which are provided with the package, or you can generate them yourself. Finally, the GSG provides a set of appendices that explain, for example, how to use the native RISC-V toolchain and OpenOCD from the command line instead of using the SDKs. RVfpga includes 20 labs about different topics. Labs 1 to 4 show how to run C and RISC-V assembly programs on the board and in simulation. Lab 5 shows how to create a Vivado project in case you want to regenerate the bit stream for the SoC to run it on an FPGA. Labs 6 to 10 show how to use and expand the RVfpga input-output system to enable the RISC-V processor to interact with peripheral devices. These labs introduce common peripherals such as switches, LEDs, 7-segment displays, push buttons, serial ports, etc. They show how to use both polling and interrupts to access memory-mapped input-output peripherals, and they show how to expand the RVfpga system to use new peripherals. Finally, labs 11 to 20 focus on microarchitecture and memory hierarchy. The labs in this part show how to understand the RISC-V pipeline and the RVfpga SoC memory system, as well as how to use or add features in the core, including additional instructions. These labs also show how to measure performance using the hardware counters. A second course, RVfpga SoC, is a follow-on course to RVfpga provided as an independent package. RVfpga SoC shows how to build an SoC from scratch and how to run the Zephyr RTOS on it, and some example programs on top of the operating system. In this slide, we provide different resources associated with RVfpga. The packages downloadable from Imagination Technologies. You can also find teaching resources developed at UCM, the MOOC course developed at edX, some papers, and we also include learning materials provided by RISC-V International in these links. RVfpga allows different uses according to the student's profile and to the knowledge level. We know of some experiences that have been had in the latest years. The first one has been done at the University Complutense of Madrid by ourselves. Second one at the University of Barcelona. We'll describe all of these experiences next. And also at the Portland State University at USA and at the Rapping Academic Center at Israel, they've had some experiences that are described in one of the papers mentioned before. The first example we show is Computer Architecture at the University of Barcelona. It's an intermediate course on computer organization for computer science students. They use different RVfpga labs. Specifically for the processor optimization part, they use labs 14 to 17. For the memory hierarchy module, they use the lab 19. For memory management, lab 20. And for the input-output module, they use labs 6 and 7. The second example is Computer Organization at UCM. It's also an intermediate course on computer organization, but here it's software engineering students. Only simulators and not FPGAs are used, including RIPs. The contents are RISC-V ISA review, for which we use Lab 2, processor design, for which we use Lab 11 and Labs 14 to 16, memory hierarchy, and input-output, for which we use Labs 6, 7, and 9. Finally, the third example is Integrated Systems Architecture, also at UCM, which is an advanced course on computer architecture for electronic engineering students. Both simulators and an Nexus A7 board are used, and the contents are RISC-V ISA, for which we use Labs 2 to 4, processor design, for which we use Labs 11 to 17, memory hierarchy, for which we use Labs 19 to 20, input-output, for which we use Labs 5 to 9, and finally, we give an introduction to SOC design using RVfpga SOC Lab 3 and 4. As a result of using these two courses at UCM, we have noticed that classes have become more dynamic, students are more engaged, and their understanding of theoretical concepts has significantly deepened. Additionally, the fact that the RVfpga course is based on a commercial open-source RISC-V processor further motivates students in their use of the course. All the materials from RVfpga adapted to these UCM courses can be found in this GitHub, where we provide all the details for each of the courses where we've used the RVfpga package. For example, for the latest example shown, Integrated Systems Architecture, you can see the 10 labs included in the course, and you can go into each of them and find all the resources such as instructions, installation guide, videos, examples, and all the exercises that the students must complete during the course. Some bachelor and master theses have also been developed based on RVfpga in the latest years. You have some examples in this slide. And in addition to the previously bachelor and master courses, some other courses are also based on RVfpga, such as the edX course we already mentioned at the beginning, a micro-credential that we teach at UCM for experienced persons in processor design, and you can find in this link some workshops, tutorials, and webinars given in the past based on RVfpga. RVfpga has also been used as a platform for research. Here you can see some examples of papers where the experimental environment is based on RVfpga. There are many ways of contributing to the project. For example, improving the documentation. An example would be a Chinese version of the documents, which are only in version 2. Creating new courses based on RVfpga. Improving the simulators. Adding standard extensions to the VIR course. Including more course, peripherals, etc. And of course, we are open to new ideas. Thank you very much for hearing my talk, and please feel free to contact me through the email in case you want to make any comment or ask any question. Thank you very much.